Our today's topic is electric charge. A number of simple experiments demonstrate the existence of electric forces and charges. For example, after running a comb through your hair on a dry day, you will find that the comb attracts bits of paper. The attractive force is often strong enough to suspend the paper. The same effect occurs when the materials such as glass or rubber are rubbed with silk or fur. Another simple experiment is to rub an inflated balloon with wool. The balloon then adheres to a wall, often for hours. When materials behave in this way, they are said to be electrified or to have become electrically charged. And we define electric charge as the physical property of matter that causes it to experience a force when placed in an electromagnetic field. There are two types of electric charge commonly carried by protons and electrons, respectively. In a series of simple experiments, it's found that there are two kinds of electric charges which were given the names positive and negative. To verify that this is true, consider a hard rubber rod that has been rubbed with fur and then suspended by a non-metallic thread. When a glass rod has been rubbed with silk is brought near the rubber rod, the two attract each other. On the other hand, if two charged rubber rods are brought near each other, they repel each other. This observation shows that the rubber and glass are in two different states of electrification. On the basis of this observation, we conclude that like charges repel one another and unlike charges attract each other. Another important aspect is that electric charge is always conserved. That is, when one object is rubbed against another, charge is not created in the process. The electrified state is due to a transfer of charges from one object to the other. One object gains some amount of negative charge while the other gains an equal amount of positive charge. For example, when a glass rod is rubbed with silk, the silk obtains negative charge that is equal to the magnitude to the positive charge on the glass rod. We now know from our understanding of atomic structure that negatively charged electrons are transferred from the glass to the silk in the rubbing process. Similarly, when rubber is rubbed with fur, electrons are transferred from the fur to the rubber, giving the rubber a net negative charge and the fur a net positive charge. This process is consistent with the fact that neutral uncharged matter contains as many positive charges proton within atomic nuclei as negative charges electrons. Electric charge always occurs as some integral multiple of fundamental amount of charge E. In modern terms, the electric charge Q is said to be quantized, where Q is standard symbol used for charge. That is, electric charge exists as discrete packets, and we can write Q equal to NE, where N is some integer. Other experiments in same period showed that electron has a negative charge, and the proton has a charge of equal magnitude but opposite sign. Some particles, such as the neutron, have no charge. A neutral atom must contain as many protons as electrons. Because charge is a conserved quantity, the net charge in a closed region remains the same. If charged particles are created in some process, they are always created in pairs whose members have equal magnitude charge of opposite sign. From our discussion so far, we conclude that electric charge has the following important properties. Two kinds of charges occur in nature with the property that unlike charges attract one another and like charges repel one another. Charge is conserved and charge is quantized. It is convenient to classify substances in terms of their ability to conduct electric charge. Electrical conductors are material in which electric charge move freely, whereas electrical insulators are material in which electric charge cannot move freely. Materials such as glass, rubber, and wood fall into the category of electrical insulators. When such materials are charged by rubbing, only the area rubbed becomes charged, and the charge is unable to move to other regions of the material. In contrast, materials such as copper, aluminum, and silver are good electrical conductors. When such materials are charged in some small region, the charge readily distributes itself over the entire surface of the material. If you hold a copper rod in your hand and rub it with wool or fur, it will not attract the small piece of paper. This might suggest that the metal cannot be charged. However, if you attach a wooden handle to the rod and then hold it by that handle as you rub the rod will remain charged and attract the piece of paper. Without the insulating wood, the electric charge produced by rubbing radially moved from the copper through your body and into the earth. The insulating wooden handle prevents the flow of charge into your hand. Semiconductors are a third class of material, and their electrical properties are somewhere between those of insulators and those of conductors. Silicon and germanium are well-known examples of semiconductors commonly used in the fabrication of a variety of electronic devices, such as transistors and light-emitting diodes. The electrical properties of semiconductors can be changed over many orders of magnitude by the addition of controlled amount of certain atoms to the material. When a conductor is connected to the earth by means of a conducting wire or pipe, it is said to be grounded. The earth can be considered an infinite sink to which electric charge can easily migrate. With this in mind, we can understand how to charge a conductor by a process known as induction. These figures are about charging a metallic object by induction. In figure A, a neutral metallic sphere with equal number of positive and negative charges is shown. In figure B, the charge on the neutral sphere is redistributed when the charged rubber rod is placed near the sphere. And in C, when the sphere is grounded, some of the electrons leave through the ground wire. In the figure D, when the ground connection is removed, the sphere has excess positive charge that is non-uniformly distributed. And in figure E, when the rod is removed, the excess positive charge becomes uniformly distributed over the surface of the sphere.